Hi, so today I'm going to be talking about how we can use weak supervision to learn a grounded neural semantic parser for linear temporal logic. My name is Chris. This is a joint work with Candace, Yen-Ling, Boris, Katz, and Andrei, Barbu. So robotic assistants have gotten pretty good. You can tell your Alexa set a timer for 10 minutes or add CoRL to my calendar and she'll do it. But there are still certain temporal aspects of language that machines are far away from being able to handle. Our work is a step towards robots that can handle commands like, anytime the cup tips over, I want you to set it back up, or always be watching the baby until I get back, turn off the lights when I leave the room. Formally, we're interested in the task of mapping natural language to structured meaning representations. So normally for tasks like this, modern NLP systems rely on training data sets of huge amounts of annotated sentences. In other words, like a much different setting to the one that humans acquire language in. Children rarely have access to negative examples or direct annotations. Instead, they learn to ground meaning in observation and experience. For example, they might hear their dad say something like, pick up your toys, and then they watch their brother begin to put away the blocks. From examples such as these, they come to understand meanings of words and how to fit them together. Our approach mimics this setting in the sense that our model learns to ground meaning and structure in an execution context. So for us, that means a Minecraft-like grid world, and our training data contains pairs of commands and videos showing the commands being executed. So I can give a quick overview of our training paradigm here, but of course complete details can be found in our paper. During training, a natural language command is given as input. It's mapped to a high-dimensional vector embedding, which is then fed to a parser. The parser proposes a LTL formula, and an executor module takes the hypothesized formula and the demonstration videos as input and outputs a reward. The reward imposes two pressures on the parser. So first, it's only going to accept formulas that are broad enough to capture the observed tracks. Second, it gives more reward to formulas that the planner finds to be more likely. This discourages the model from producing overly broad formulas. For the executor I just mentioned, we use a pre-trained planner that maps LTL formulas to action sequences. We also use a generator module which reproduces the original command. This is a standard multitask learning technique, and it encourages the model to conserve information about the input command and its embedding. We run two experiments. So in one, we have sentences which were generated mechanically from a context-free grammar, and in the other, we have sentences which were produced by humans who annotated the demonstration videos with the commands that they thought would have elicited the observed behavior. We train using two methods. First, policy gradient using the reinforce algorithm, and iterative maximum likelihood. We evaluate on metrics to get a sense of how good our parses are. So first, an execution metric that measures the fraction of formulas which accept the demonstration trajectories. Note that this is going to be an overestimate of our output quality, since mere acceptance does not require understanding. So we also measure the fraction of formulas that the planner executes correctly on. This is an underestimate of performance, because even the ground truth meaning representation is not always going to induce the correct behavior from the planner, which is itself a neural model. As is the case for many language tasks, no single metric will give a complete picture, but these two metrics provide a good upper and lower bound for performance. So we compare to a fully supervised baseline and find that a good portion of our performance is recovered by the weakly supervised approach. In the case of the plan metric, we even see an increase in performance. For the human annotated commands, we see things decrease slightly, but still much better than random chance. And of course, this is to be expected since the human command dataset is taken from a much larger vocabulary space. Taken together, we believe that our results serve as an encouraging proof of concept. Many problems in robotics and NLP could be tackled by such an approach because of its low requirement for annotation. Being able to adapt to variations in language use and to changes in the environment is crucial to building useful robots, because the same language may carry very different meanings in different contexts. In the long term, we hope that this line of research leads both to robots that understand us and to robotic systems that can be used to probe how children acquire language, thus bringing robotics and linguistics closer together. Thank you for your time.